I'm Tony Latempt, Principal Software Engineer.
I'm Dan Daemon, Principal Software Engineer.
We're from Walmart Labs, and today we're going to present on LLAP and Hive, Fast SQL and Hadoop. Really? The agenda for today's presentation will give a brief intro into Walmart Labs retail. We will discuss how Hive is used at Walmart Labs retail, give an overview of Hive LLAP architecture, and then an overview of the Hive LLAP POC that we performed, and if time permitting, a Q&A at the end.
So who we are, we're a division of Walmart Incorporated. We're a Fortune 1 company. We serve 260 million customers on a weekly basis. Yeah, we've got over 11,500 stores under 59 banners in 28 countries. We have e-commerce presences in 11 of those countries. So Walmart Labs currently employs more than 4,000 associates worldwide. We have development centers in the US, Brazil, Ireland, and India. And our mission statement is quite simply, we're here to help people save money and live better.
Hadoop at Walmart. So Hadoop first came to Walmart in 2010. It started out as one cluster with 12 servers. Since then, as of 2018, it has grown to 20+ clusters and thousands of servers. Some of the products that we support on Hadoop are sales and marketing, back office application, inventory, IoT, and enterprise data lake.
So right now, how is Walmart actually using Hive? So our predominant usage right now is using Hive MapReduce. Since we've actually exposed the Hadoop platform to a wider arrangement of users, company-wide, most of the default that come in goes directly to MapReduce. We've got another large segment moving to Hive TES, about 30–40%. Most of the interfaces that are currently being used are Hive CLI for those comfortable with that environment, Beeline, a native ODBC or JDBC drivers, and a lot of the newer people coming on our platform are really heavy into a visualization tool of some kind. So this is kind of a little chart on what we call our Hive user community. In the lower left quadrant, these are the folks that have been running on EDW platforms for years. They usually have a visualization tool. They have pre-canned queries, do very little adjustments or anything off of that. And they're told that we presented with far more data than they're used to having. So they come in, lift, place the query on the Hadoop platform and try to run it at that standpoint. We've also got people as they gradually grow up, get more and more based into using SQL, highly nested loop joins and such, until they transition fully to an HQL type of environment. As we move farther to the right, we start getting into the more technical users, the developers, data scientists that will use various platforms, R, Python, developer Spark, and then we get a convergent up at the top for those that are actually really into both aspects of the job. So we get general feedback from our users when they're actually exposed to Hive for this first time. And I go, 10 years of data is great, but can you make it run faster? It takes too long to iterate through a process, just too slow.
Other feedback we get are, my queries are slow, and my query runs on blank fill-in-the-blank platform here in way less time. So enter LLAP. LLAP, huh? LLAP, low latency analytical processing, or my favorite, live long in process.
So carrying on, what is LLAP? LLAP is the next evolution of Hive. It consists of long-lived daemons that's running across Yarn. It's tightly integrated with the DataWorks or base framework. It does the caching and prefetching as well as doing query fragmentation execution all within the LLAP daemon. And it also works well with the JIT, just-in-time optimization. So we stepped into an LLAP POC goals with essentially to answer two questions. Is it fast? And that's compared to your Hive TES or Hive MapReduce. And then how does it scale? So some of our initial settings that we had on our on-prem clusters is we currently have impersonation on. So we extensively use the Resource Manager Web UI. It's to find out who's doing what, where, and such. We have preemption off, as we have had incidents and issues where we've encountered preemption killing jobs prematurely, especially Uzi launchers. We have Fair Scheduler. Well, we liked it. And we're not using node labels at this time. And really, our LLAP nodes that we've actually targeted for this POC, it consists of 256 gigabit RAM, with 32 CPUs, 15 6-terabyte drives, and we're running currently on a CentOS 6 framework OS. So we started also on this with a series of assumptions. All memory that we're dedicating to an LLAP server is going to be used to cache the data. LLAP will use impersonation. From a user perspective, every one of my queries is going to be fast. And we thought we could still continue to use Hive CLI. And since our clusters are highly multi-tenant, LLAP will adapt into it easily.
So now we're going to start diving into LLAP. And one of the first things we want to discuss is what happens with a query with or without LLAP. So on the right, without LLAP, you can see the coordinator, the application master, asks Yarn for containers. The coordinator pushes task attempts into containers. And then the record reader is used to read data. On the left, stage left, with LLAP, the coordinators locates LLAP resources via Zookeeper. The coordinator pushes task attempts as fragments into LLAP, and then the LLAP I/O cache is used to read the data if the data is already cached, or the record reader is used to read the data if the data is not cached or cannot be cached due to file format. Here's a visual that gives a graphical visual of the architecture of LLAP. One of the things we really want to call out is that LLAP runs in Yarn, and that is one of the reasons why we like it. From Yarn's point of view, it is just another application. So the end user submits the query via ODBC JDBC. A query coordinator is spun up. The query is pushed to the LLAP daemons as fragments. Another key thing we want to call out is that the data that is cached for a query in the LLAP daemon can be shared across all other queries. So in other words, if query 1 brings some data into memory, into cache, and then query 2 comes behind it and needs the same data, it can read that data that's already been cached. It doesn't have to recache it for itself. Another thing we want to call out is that the data does not have to be local to the server where the LLAP daemon is running, because LLAP is another application in Yarn. So if that data exists on another Hadoop node in the cluster, another data node in the cluster, the LLAP daemon will fetch that data just like any other Yarn application and then process the query. The storage that is supported is HDFS and compatible, S3 WASB, and Isilon as of this chart. Diving a little deeper into the LLAP daemon, again, an LLAP daemon runs in a Hadoop cluster. It runs inside a Yarn, so we have a node manager there. We then carve out a certain amount of memory of that node manager, and we give to the LLAP daemon where the query fragments run. And then also we carve out an amount of memory for cache, and this is where the column data is cached and the metadata is cached. So for our POC, the first thing we did is we went and we generated 200 queries looking at different time intervals, 1 day, 1 week, a month, 3 months, 9 months. The first set, we just looked at 4 months of aggregated data with these 200 queries, and we ran them with Hive MapReduce, Hive TES, and Hive LLAP. And that 4 months of data was around 400 gig. So first, over here, the overall LLAP ran over 50% faster than TES. TES is in the blue and LLAP is in the orange. At the far left is you're looking at the smaller amount of data, and all the way to the right, you're looking at the larger amounts of data. So as you move this way, you're processing more data. LLAP versus MapReduce, it wasn't even a competition. LLAP was over 90% faster. So with that, it's goodbye MapReduce. Aw, you served as well. So then we said, okay, let's take those 200 queries and let's run them against 9 months of aggregated data, because that's one of the things our customers usually do is they try to look at close to a year's worth of data. At this point, this data set was 1.2 terabytes of data. So before we get to the graph, we want to call out some parameters that we tuned specifically for this POC. We ran on 10 LLAP nodes, and you can see we had run 1, run 2, run 3, run 4, and each time we were iterating through the process, tuning this, tuning that, and what we're trying to do is balance the amount of concurrency, or balance the amount of data that we can cache with the number of parallel threads that we can get. And so you can see that it was very much a tuning process, and at the end, this is what we ran on with the 10 nodes. So LLAP versus TES, those 200 queries, again, the far left, 1 day, all the way to the far right, 9 months. And LLAP ran in approximately a third of the time of TES. It was amazing. So then we said, okay, let's scale LLAP up to 30 nodes. Now what I'm going to attempt to do here is walk through the formula to figure out what these values should be set to. We will also have the formula in the presentation as a slide, so if you need it, you will have it. But basically, the amount of memory that we give to the node manager, all this is in meg. I'm going to convert to gig, but it's all in meg here. 225 gig we give to the node manager. And through our test, we realized that we have to actually account for 2 application masters per LLAP daemon. You have the slider application master, and then you also have the TES application master for the task. So if our slider application master was 2 gig, the TES application master was 4 gig, that's 6 gig total. 225 minus 6 gig is 219 gig. So now we have 219 gig that we can give that is memory per daemon. So then we're looking at the number of executors and the executor size. Our testing, we found that the best executor size, which is, think of an executor as essentially the containers, is 4 gig. So if we're going with 40 executors, 40 times 4 is 160 gig. So we can then take the 219 minus the 160, and then we also have to account for the max headroom, which at the end here was 6 gig. That leaves us with 53 gig for the in-memory cache per daemon. So of the 225 gig that we're giving to Yarn per server, only 53 gig is going to actually cache column data and metadata. So how did our aggregated query perform with 30 nodes?
As you can see, we actually, when we compared with these 2 runs, and moving again from the left of the chart with 1 day all the way out to the 9-month aggregation, saw that we got about the same performance pattern that was exposed off the 10 LAP nodes. So we got overall, a 1/3 processing less time. And if you look at the number, it doesn't quite show real well, but under the 30 nodes, all the queries finished in under 3 minutes each. Whereas with the 10 LLAPs, they were running under 9 minutes. So from a recapping of the aggregated query performance, running the whole workflow on 10 LLAP nodes actually reduced the overall time by 68%. And that's a gain over TES. When you took it to the 30 nodes, that dropped it by 80% over TES. And you can tell the comparison between all three runs.
So then we went to our users and we asked for queries that were representative of their workload. And we wanted non-aggregated queries, i.e. queries with joins. So they gave us a sample set of 48 queries that have at least a minimum of 4 joins in them that are looking, again, at a time interval. We start at a very small time interval and work our way all the way up to 51 weeks of data. The total amount of data processed in this was 1.3 terabytes. So, non-aggregated TES queries. So you see the blue line in TES is going and going, and then we stop. TES was able to process all the way through the 12 weeks, but when we got to 51 weeks, we could not get it to process. We had errors. We did some minor tuning, and then we said, you know, this is a LLAP POC. We're not going to continue tuning TES. Quote, unquote, out of the box, LLAP was able to process all 51 weeks. And again, you can see how dramatically faster LLAP is. If we deep dive into the LLAP response times for the non-aggregated queries, we can see that 1 to 12 weeks ran in less than 2 minutes, and 51 weeks ran in less than 9 minutes. So doing year over year on 10 nodes, less than 9 minutes. And these were complicated joins looking at the scan level for our retail merchants customers.
Again, carrying this out to the 30 LLP nodes, we saw that, again, a dramatic improvement in the performance over just the 10 LLAP nodes, and then completely out of the water with TES. But again, it's about a third of the runtime. And again, was showing even with the 51 weeks of the non-aggregated data queries, they're all running still in under the 3-minute time frame compared to the 9+ minutes on the 10 LLAP. So given the scale, it shows that we can scale out accordingly with that, adjusting the memory accordingly. So on a recap of our non-aggregated query performance, taking LLAP 10 nodes over TES, we got a 60% performance improvement overall. That actually, taking the 30 LLAP nodes, it actually improved to 80% over TES. Now the big call out is the TES, the sample queries we were provided, actually quit running essentially once we started getting into the year's data.
So we then decided, as part of the POC, to do a concurrency and a multi-user test. We wanted to see how does LLAP handle concurrent users and multiple users. So first we took 1-day query, so only looking at 1 day's worth of data, and we ran it 1 time. You really can't see it on this chart because it's just 1 point. And then we looped that very same query and ran it 5 times. And you can see that, so the first query ran in 9.8 seconds. We looped it and ran it 5 seconds. And you can see a slight uptick, but within seconds, I think it's like 10 to 12 seconds. We then ran it and looped it 10 times. Again, you can see that uptick starting to get higher. Now, what's happening here? Well, the more queries we run at the same time, the more queries are having to fight for the same set of resources, right? We only have 10 nodes. We only have 219 gig for the containers. We only have 53 gig, or on the 10 nodes cluster, I think it was 48 gig at the time, to cache the data. We then ramped it up to 20 nodes. Again, the same query, just deliberately spinning it up faster, or more and more and more. And now once we get past 10 nodes, what you're seeing here is we're also introducing wait time. Because in our parameters chart, and I don't know if we called it out and we can go back during questions, we actually set the number of concurrent queries to 10. So once we get beyond 10 concurrent queries, we're also introducing wait time. So the more queries, the more wait. And you can see ultimately with the 40. And you can also see the downtick roughly corresponds to about 9 or 10 seconds. Each query runs 9 to 10 seconds, so you can see that wait time manifesting. So then we said, OK, let's do what our users normally do, which is things we completely don't expect them to do. So we deliberately took queries and ran them helter-skelter, the same 200 set of queries, but batched them to run 1 at a time, batched them to run 5 at a time, to run 10 at a time, 20 at a time, and ultimately 40 at a time. And what we're trying to show here is sort of a random access pattern. And you can see the orange is 1, the dark blue is 5. It's worse than the orange, but it's still pretty good. And then the gray is 10, and then 20, and then 40. And you can see by the time we get to 20 and 40 users, the performance definitely degrades. By the time it's in the 40 users, it's around 10 minutes for the queries. Now, one thing we want to call out is that looks really bad here when compared to the orange and the dark blue lines. But if we go back, those peaks are actually close to what the queries in TES were doing when we were running them just 1 at a time. So even though it's not good for LLAP, and I'm pretty sure our users wouldn't be terribly happy with it in the moment, it actually is showing that, you know what, still overall, and compared to where we were with TES, it's actually doing really good on those queries.
So that brings us back to our starting set of assumptions for the POC and the actual reality. So from an administrative point of view, we started off saying that all memory can be allocated to LLAP containers and can be used to cache the data.
No, only 52 gig of the 230 gig allocated to the node manager goes to caching column data. There's a big difference if I've got 30 nodes between 230 times 30 and 50 times 30. It's a very important point.
Our second assumption was LLAP will use impersonation.
No, the containers run as Hive. We now have to use the TES views to see what the end users are doing. So this is new for us. Now we have to go and provision new servers for TES views. It's a new tool that we have to learn, and it's a new tool that our users have to learn.
Now, from the user perspective, all my queries will automatically be fast.
No, poorly written queries will still perform poorly. Case in point, we turned it over to our users, and they promptly went and queried 10 years worth of scan data, joining it by no partitioning columns, and looking for each register. So no, poorly written queries still perform poorly.
But we're still able to use a high CLI if we choose to, right?
No, only Hive Server 2 connections, aka Beeline.
Now, the last one, most important. Our clusters are all multi-tenant, and LLAP adapts nicely to that.
No, right now there is no real workload manager for LLAP. So as the previous slide showed, it really does not handle multi-tenancy. So some of the architectural changes that we made for LLAP, first, impersonation off, which we weren't terribly happy about. Preemption on, but one of the good things, we only turned preemption on at the queue level, so we can control where preemption is happening. Node labels a must. Actually, that one we were pretty cool with. We didn't fight that one. The capacity scheduler, we were quite happy with our fair scheduler. We loved it. And LLAP will run on the fair scheduler. Hortonworks would not support us on the fair scheduler. Glaring at Hortonworks right now. So we have migrated to the capacity scheduler. But with the capacity scheduler has evolved to where now you can do the fair policy at the queue level. So even though we glared at Hortonworks, we actually accepted it rather mildly. Dedicate node managers to LLAP. Do not attempt to run other processes outside of a data node. But do not attempt to run other processes on the nodes that you're running LLAP. You want to try and avoid the noisy neighbor problem, Remember, of that 230 gig that we were giving LLAP, really only 53 got the cache data. If you really want to get the most out of LLAP, he really needs to have all of the resources as possible on a node. Where do we go from here? So we are currently deploying LLAP to other clusters. We actually just deployed it to another production cluster, so now it's in 2 production clusters. However, the other production cluster is very single user mode. The workload is very focused, and we know that we can control it. We are still investigating multi-tenant workload management for LLAP. We do know that a workload manager is in the roadmap. We can't wait to see it. Currently, we deploy LLAP inside of a cluster, and we're researching whether it would be better, and right now we kind of think it will be, but we have to test this out, to deploy LLAP in the cloud as cloud clusters, use our on-prem clusters to generate the data sets, push them to the cloud, spin up little LLAP clusters, and then we can isolate the users from each other and avoid that horribly messy slide that we saw a few slides back. And also on the roadmap is SSD caching for LLAP. So we would like to thank Pardeep Kumar, our Hortonworks system architect, senior systems architect, who worked very, very closely with us on this POC. Without it, we would not have been able to complete it, without him. I'm Tony Lieutenant.
And I'm Dan Neiman.
We're open for questions. Can you go to the mic? They want people on the mic because they're recording it.
Thanks for the recommendations around how you should set up LLAP on a single node. I guess I've got 2 questions. One would be, when you had 10 nodes versus 30 nodes, would you say like that was like a percentage of the cluster size? And then also related to that, because you had 20 plus clusters, are you only caching one data set inside of LLAP? Because we're a little bit nervous that we're going to have crazy cache invalidation, and you're basically just going to be doing record reading the whole time.
So the 10 and 30, that was 10% of a cluster. And are we caching only one data set? No, because remember, we're giving it 53 gig of memory, so whatever they're querying can go in. But I think the broader question you're asking is, well, what about finance runs their queries and then HR comes behind them? And that's exactly what our warning is right now. There's no real good way to handle that.
So just to add to that, it's Pradeep. So related to caching, right? You can't pre-specify this data has to be cached. Okay. So what LLAP does,
can't pin it to memory.
Right? What LLAP does intelligently is that it doesn't cache all the data. For example, you're joining on 2 tables, employee and department, on employee ID on both tables, right? So what happens is that only first it caches the metadata. Only the metadata for the tables in the query. Based on the metadata, it drives which blocks have to be cached. And specifically for those columns, only it will cache the data. So for employee and department, if you are using employee ID and department ID, those are the only 2 columns which will be cached. Okay? And the next time when someone files a query, right, and on the same table, employee ID table, and employee table and employee ID and another column from that query, it will recache only the missing column, not the column which was already cached. And it uses least recent frequently used algorithm, right? So basically, our data which is cached data which is not being used in any query, it will be evicted. So,
and one thing we should have called out here that's very important is it also has to be ORC file formats. They are adding other file formats in the functionality, but if it's not, the query won't fail. It'll just run for a really long time. And so that's another thing that we're having to get our users to move to, and that was a big, I wouldn't say hindrance, but some of them had already started using ORC, some aren't, some were using Parquet, Hive RC, all over the place. And if you really want to take advantage of it, those tables need to be in ORC. So that's like pre-work you have to do before you can take advantage of it.
Nice, thank you.
Any other questions?
So I have two questions. The first one, the plots that we saw, were those comparisons done on subsequent runs on LLAP? Because first time the caching has to be done, right? So TES versus subsequent runs on LLAP, were those plots on after the
TES
caching?
versus LLAP?
Yeah.
Well, so they
Because
were...
the first time we run, nothing is cached, right?
Yeah, but TES isn't going to take advantage of caching, right? I mean, so traditional, Hive traditional TES isn't taking advantage of caching. And the way we did it, so when you set up LLAP, you set up a queue specific for LLAP, right? So we also had a queue that was sized exactly the same, where we ran the TES jobs and the MapReduce jobs. And so we just kicked them off. We had the whole workload run, you know, one from 200, one from 48. We let those run. And then we went and ran them in LLAP. And we did not pre-warm LLAP, right? We just like we did with TES, we started on the first query and ran the whole workload through.
So basically, we know that you know, the first time you run any query, right? The containers are not pre-warmed, like that nothing is cached in there, right? So when you run second time, the queries will be faster, but that will not be apple-to-apple comparison with TES. So all the tests which you are seeing here are the queries for the first runs.
And the 200 queries, also we put both through their paces, because the 200 queries, we're looking at, you know, a week, a month, da-da-da-da-da. But within that, we also had the queries broken out to where we were looking at different predicates. So it wasn't just that, oh, well, we warmed up LLAP because the first day query, and then, you know, the week, and then warmed up the month, and so on and so forth. No, because we deliberately also played with the predicates too. So the first 20 had 5 different versions of the predicates, so on and so forth.
So with the LLAP, the engine was TES, or?
Yeah,
the engine is TES, but it's, so LLAP runs in TES containers too. And then we also tested it against Hive traditional TES with no caching.
So think of LLAP as Hive on steroid.
Exactly,
you know?
exactly.
It is the evolution of Hive.
It is TES. It is pre-tuned, pre-cached. Like if you think of TES, right? When you run a query, a new container spins up. There is heap allocation. There is cache allocation within that container, which can't be shared by anything else. So JVM initialization, all those things. What TES does, what LLAP does is, it is again a TES job, TES container only, which is a large container, right, which is always running, long running, right? So every time you don't have to spin up new container every time you run a query, and it has dedicated cache and heap allocation.
Okay. And can Spark take advantage of LLAP?
Yes. So Spark 2 can directly query, can connect to LLAP.
And you
From
can,
Spark 2, not from Spark 1.
You can see here the number of concurrent queries was 10. That's what I was talking about in the one chart where when we got above 10, we started to introduce wait time, which makes sense because we had told it that the concurrent queries was 10. And we've got the formula at the end of this presentation and the parameters. So if anyone downloads it, they can do it. And another thing we want to call out with this is it's very iterative. As we're deploying it to this next cluster, we're going through these parameters again and thinking, you know what, we can tweak this, we can tune that. This workload's slightly different. They use different tables. So it's not gospel, but it's a place to start.
But this run third will give you kind of, for this hardware profile, will give you kind of best optimized performance for general workloads, unless you're running into specific workloads.
Any other questions? I think we have a few minutes.
One over here.
Here's the formula.
First thing, excellent presentation. So it
Oh,
was
thank you.
very informative. I'll ask a question which is in a lot of people's mind. Is LLAP there where we can replace with Teradata or something like that?
No.
How close the performance?
The whole multi-tenant thing, no.
So it is.
It will maybe.
It depends, right? So I'm architect, so my answer is depends, right? So the question is, if somebody comes to me, like some customer comes to me, for example, say that, hey, I want to replace Teradata, but they got just like 5 nodes running on Hadoop, right? And you can't replace that. Look at the cost you're spending on Teradata or SAP HANAs of the world, and the amount you spend on Hadoop, right? If you can, let us say in this case, if I have SSD hardware, and if I have like 100 nodes, LLAP cluster, and some of the queries which we picked from SAP HANA, I think we can if not defeat in the query performance, we can be comparable. Because some of the queries you are seeing like completing in 3 minutes, complete in almost a minute and a half in SAP HANA.
Yeah, it also goes on cost benefit. So
right.
if my cost of paying on Hadoop is more than Teradata, then it will not equate out. So
correct,
performance.
Correct.
So I'm asking that
Correct,
respect.
correct.
If there was any.
So you have to do. Yeah, go ahead.
Well, so one of the things too to point out is a lot of data that's generated in our Hadoop clusters. What ends up happening is there's a very real business need for the Hadoop cluster, right? There's an operational thing that needs to happen, right? And it generates this data. And then you get all these business users that are like, wow, I have all that data that I wanted in one place. That's awesome. And they swarm to the cluster. And they consume huge chunks of resources. That workload that they're coming to Hadoop anyway because that data is there. But now they expect performances, to your point, like Teradata and HANA and whatever. Well, they're expecting that on Hadoop. If we can take that workload and potentially, like I said, spin it up in a cloud LLAP cluster, small little ones for each of them, and let them run there, and then we relieve the pressure on the operational cluster so that it can do what it needs to do, which is generate the data they all want to query, then we're saving them from either having to go move the data back to Teradata or move it to HANA or whatever, or ThoughtSpot or any of the other tools. We're not endorsing any of those tools. We're saving that movement of the data, right? They're able to, it's generated in Hadoop, and they can now query it in Hadoop at really fast times.
And one of the things you have to also look at workload management, how that evolves, right? Because one of the issues which we saw with LLAP was those multi-query runs, right, concurrently, that there is no dedicated sharing of resources, or you can say that this user can take this much resource in LLAP queue, and this user can take this much, right? As that evolve, and as you see SSD caching, all those coming to picture, I think that could be time we could start comparing these, but I think this will be too early days for this one.
No, that's what I thought, but I just wanted to still ask the question.
But it definitely is very exciting, and it is the evolution of Hive. And we've seen improvements in it. We started the POC in December, and as we were working on it, we saw it improve.
And you know, some users might not require the performance like Teradata, so they can be moved to LLAP versus some user really requires. So it all, and the concurrency.
Yeah, and it also comes down to architecture, right? You can create like pre-materialized tables in Hive itself, LLAP itself, and get that kind of performance. But there are like tons of cases you have to architect based on what you want.
I really think the non-aggregated charts that we had are really the most powerful. The aggregated you would almost expect, right? That's kind of a softball we tossed. But the non-aggregated, joining all of that data, and the speeds we were able to get for that was really amazing. And our business users were very excited about that because they came to us specifically and they said, we want these year over year, these 48 queries, and we want them to run in this time. Our goal they gave us was less than 5 minutes.
Yeah, I can think of a lot of supply chain users who can use the LLAP concept. Yeah, okay, thank you.
I think we can take one more question.
Yeah, so in traditional Hive MapReduce, if one of your queries goes awry and you want to kill it, you can just kill the yarn container. How do you kill a query in LLAP?
That's what we're looking at. Yeah, so there's a way to
We were
do
doing
that.
this earlier.
So there's a way to do that actually by killing that yarn application ID, which it will be running, right? And what it does is that since it runs on slider, it will actually spin up that application master again.
In the TES view, you'll see the DAG ID.
So think of LLAP. So you have to know how many queries you want to run concurrently. So let's say you say 10 queries, right? So there will be 10 pre-spinned up application masters. Each of application master will run one query, right? So the query which you want to kill, you have to kill that application master, and then slider will automatically spin that application master again.
And you can find all of that in the TES view.
TES UI has, so basically Hive Server 2 LLAP has another UI.
Okay, so you don't have to bring LLAP all the way down.
That's
just
right.
kill
No.
that one.
That's right.
Okay.
No.
I think probably you got into that incident where you killed slider application master itself.
Yeah, once you kill the slide, you do, which we've done. You then have to restart the whole thing. All right, if there aren't any other questions, thank you very much.